As we start looking at some applications of graph theory, we're going to start with some topics related to optimization of travel through a graph. So as we're thinking about how to move through a graph in an optimal way, we've talked about things like the traveling salesman problem, which we'll come back again here in just a minute. But um, as we talk about that, we need to have some sense of the cost of moving through a graph. In other words, each edge should have some sort of cost associated with it, which might be, for instance, a distance that you're traveling to move from one location to another. So the terminology we use is a weighted graph, and a weighted graph means that we give a weight to each edge, and you can think of that as, again, the cost of traveling along that edge. So if you think, for instance, of a map like this, we can think of the distance between cities as the cost of traveling there. So if you want to visit several cities on this map, you would have to account for the distance that you have to travel to get from one to the other. So if you were going to visit LA, San Francisco, and New York, you wouldn't go from San Francisco to New York to LA. It would be much more efficient to visit San Francisco and LA and then go to New York, for instance. So that's kind of the idea, is that we have some cost associated with moving through this graph. And so we're going to think about a couple of different problems that come out of this. What kind of things we might want to figure out, and we'll talk about that in a second. But here's another example of a graph with weights on it, a weighted graph. So this might be a portion of downtown somewhere where Google Maps has a graph that describes roads that you can travel on or paths that you can walk on, whatever it is. And as it tries to map out the most efficient route from the start to the end, it has to account for how long it's going to take to travel from one point to another. And so as it finds the optimal route, maybe these weights are the amount of time it'll take to travel through each of these. And so Google Maps keeps track of traffic, for instance, and with traffic data can update these weights. And if there's congestion, it might increase that weight, and then that would direct traffic away from that segment, for instance. So the goal is to find the most efficient path from the start to the end with whatever weights you have available. So Google Maps has a tremendous amount of data that it has to keep track of. The graph itself, first of all, like what edges there are that connect one node to another, and then it has a constantly updating grid of weights associated with those graphs that has to account for things like traffic and closures and so on. So there's a tremendous amount of data, but we're actually going to talk about how Google Maps and other navigation systems find the optimal route from point A to point B. We'll talk about that a little bit later. So kind of the two questions that we're interested in with these weighted graphs is, if we wanted to visit all of the nodes exactly once as efficiently as possible, this would be the traveling salesman problem, where our goal is to visit everything, but to do so as efficiently as possible. We've talked about before how there's no general solution to this to find the absolute optimal path, but there is something called the nearest neighbor algorithm. And the nearest neighbor algorithm is not perfect. It doesn't get you necessarily to the exact optimal path, but it is one way to get a good result. So it gives you a good result. It may not be the best result, but it'll give you a good result, and it's pretty easy to run. So it's a fairly efficient algorithm that gives you a decent result, which in a lot of applications is about all you can expect, and certainly good enough for most problems. Then the other question is, if we're not interested in visiting everything, but we're interested in getting from one point to another, how do we find the shortest path? And the algorithm we'll talk about here is called Dijkstra's algorithm. This is a famous algorithm, and it forms the foundation piece for all of the navigation algorithms that are out there. There are a handful of variants, but they're basically offshoots of Dijkstra's algorithm, and they kind of add things to them. So Google Maps uses one called the A-star algorithm, which is basically Dijkstra's algorithm plus a little bit of fancy addition. Basically, it adds heuristics to the algorithm to improve it a little bit, but the foundational theory is Dijkstra's algorithm. So it's very practical. The algorithm itself, once you get the hang of it, is not really that complicated, which is good because it makes it efficient and makes it work pretty quickly. So these are kind of the two big questions. One is, if we want to visit everything, how do we do so efficiently? We'll talk about the nearest neighbor algorithm. The other one is, we're not interested in visiting all of them, we're just interested in getting from point A to point B as efficiently as possible. And we'll talk about Dijkstra's algorithm. Dijkstra's algorithm does give the optimal result, which is good. So it doesn't just give you one that's good enough. You can take shortcuts and find ones that are decent if you want to save yourself some time, but those are all more complicated variations on it. So just to keep track of these two things, I like to think of the first question as kind of the UPS problem. How do you visit all the locations you have to visit to drop off your packages, for instance? And then the second one I think of as the Google Maps problem. How do you get from point A to point B as efficiently as possible? So we'll talk about both of those each in separate videos.